All right, we're going to pick back up where we left off. Whatever the last time I saw y'all was Friday, I guess. Yeah, I think it was Friday. And we're going to kind of make some videos for the stuff that we probably should have gotten to on Friday and that we really need to get to today. This is probably going to take a little bit of time, but that's okay. Just some videos. Watch them, rewatch them at your leisure. Here we go. Stop back. Remember last time we talked about the radius and the interval of convergence. That interval of convergence is basically, hey, how long, what window is that polynomial or is that series going to hug that function pretty closely? And then eventually it gets to some point where it kind of breaks off, it diverges away from your function's graph. And really, if your series is divergent, it's not very helpful, right? We wouldn't want to use it as an approximation because the graph, right, it's peeled so far away that you would have just been better off just probably randomly guessing a number. But as long as that series, aka as long as that polynomial is convergent, then you know that the graph of that polynomial is going to hug pretty darn closely to the graph of that function. And so therefore, our approximations using the polynomial are going to be pretty good. We can always make them better by adding more terms, which also widens the interval. But we have that little interval where that series is useful. That's the radius and the interval of convergence. Again, the interval is kind of the whole range of x values, and then the radius is from the center, how far to the right, from the center, how far to the left, right. What's that wiggle room that we have? Remember, it's always going to work. It's always going to converge at the center. And then I can add the radius to the right. I can subtract the radius to the left, and then that's going to give me my framework for the interval of convergence. And then we always have to test the endpoints. We have the three different scenarios that unfolded. Sometimes we have a series or polynomial that converges for all real numbers. Somehow it just always works. That's kind of rare, but it happens sometimes, and it's going to happen today with the ones we're going to look at first in the notes. Other times you have a polynomial that really is going to almost always diverge, but there will always be the one point where it works. It'll always, always, always converge at the center. The graph of the polynomial and the graph of that function will always be very close to each other right at the center's value. Okay, now the question is, does it work at any other places apart from the center? If that radius is infinite, so if it extends infinitely to the right and infinitely to the left, then your interval is from negative infinity to infinity. It converges for all real numbers. That happens sometimes. It's rare, but it happens. Sometimes we have the instance where the radius is 0. So that's when it only works at the center, but it doesn't work anywhere to the right or anywhere to the left. The interval is really just that one singular point at the center. Most of the time, though, we're going to have the interval. So from the center, extend the radius to the right, extend the radius to the left. And remember, you always need to test the endpoints. Take the x value on the left, plug it into the original series, see if it converges or diverges. Take that x value for the endpoint on the right, plug it into that original series for x, see if that resulting thing converges or diverges. We have those 10 tests from the previous packet that we used to determine if that endpoint ends up converging or not. So that's what we did last time. We finished with the radius and the interval of convergence. And today we're going to kind of be looking at some specific MacLaurin series and then a couple of manipulation techniques based on them. And we're going to start off by kind of finding this Taylor series for f of x, which is e to the 5x centered at 2. Again, the only difference between a series and a polynomial, the polynomial stops, right? It could be a second degree, so it stops with the term that has an x squared, or it could be a fifth degree, so it stops with the term with the x to the fifth. The polynomial is eventually going to have a biggest term, and then it's going to stop, and it's not going to go on any farther. But the series is going to go on forever. So typically for the series, you'll see like the first 2 or 3 terms written, and then you'll see that little ellipses, the plus dot, dot, dot. And then we'll see the general term, right? Here's our general term. And then after the general term, it keeps going, plus dot, dot, dot. Series goes on forever. It's the sum of infinitely many terms. But these Taylor series are going to be built the same as the Taylor polynomials were. Remember, every little piece has the 3 different chunks. You have the nth derivative chunk. You have the x minus c to the nth power chunk. And then you have the n factorial chunk. building the series versus building the polynomial is really the same, except we're going to need, for the series, we're going to need the general term, and then we'll put dot, dot, dot afterwards. All right, so let's go for it. We're going to build a Taylor series for this function e to the 5x. First thing we're going to need is just to take some derivatives. So let's go for it. We have f, which was e to the 5x. Let's just go take some derivatives. Okay, so it would be 5 e to the 5x. Then the second derivative would be 25 e to the 5x. And the third one would be, let's see, 125 e to the 5x. Does it tell us how many terms? It says 4. We have the original function and then 1, 2, 3 derivatives. So methinks that's probably going to be enough. If we wanted to go more, we could keep taking derivatives. I'm not gonna. Okay, so it would keep going, but we're done. So we've taken the derivatives. Remember, now we would need to evaluate them at the center. So at x equals 2, and then that's going to give us 1/3 of what each chunk is going to look like. So that's going to be e to the 10th, 5 e to the 10th, 25 e to the 10th, 125 e to the 10th. The next one would be 625 e to the 10th, dot, 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 right? We can keep going. Let's think about what our nth derivative would look like. I'm going to go a little bit into this next question. That's okay. What would the next derivative look like? Because we're going to need a general form also. So let's think. We have that first one is just 1 e to the 5x. Then we have 5. Then we have 25. That's really like 5 to the 0. That's 5 to the first, 5 to the second, so on and so forth. So for thinking about it, all of these derivatives, of course, going to have that e to the 5x, but it's really going to have 5 to the nth power as that coefficient. And you start with the 0th derivative, so 5 to the 0, that's 1 e to the 5x, then 5, 25, so on and so forth. So there's our general term. It's going to be a 5 to the n times e to the 10. Okay, so there we go. There's our general form for that nth derivative. Now we need to tack on the stuff that we need to tack on, right? We're going to need the x minus c piece and then the factorial piece. Let's kind of add that stuff on, or tack it on, really, it's multiplying. So that one's going to be multiplied by x minus 2 to the 0th power over 0 factorial. But x minus 2 to the 0 power, that's 1. 0 factorial is also 1. So really, for that original function, right, the n equals 0 term, we literally don't need to tack on anything. But everything else we will. Here we go, x minus 2 to the first over 1 factorial. Remember, you don't have to write 1 factorial because it's 1, and you don't have to write to the first power. So we're just going to tack on the x minus 2. That looks like an underscore, and it's going to bother me, so I'm going to fix it. X minus 2. You don't really have to put to the first over 1 factorial, although you can if it makes you feel all warm and fuzzy. The next one, we're going to need the x minus 2 squared over 2 factorial. And then at the next one, I would actually leave that. 2 factorial is 2, so I would leave it as 2 factorial. The next one, I would leave it as the factorial, because that's going to help you see the pattern. Here we have x minus 2 cubed over the 3 factorial, and then dot, 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 right? This one is going to be x minus 2 to the nth over the nth factorial. Okay, so we kind of took our derivatives, we evaluated them at the center, we tacked on the x minus c piece, and then we tacked on the factorial piece. Let's just kind of collect everything together, and let's write an expression for this. Let's write an equation for this Taylor series. A lot of the times for the Taylor series, you're going to see it written as like t of x. Right? You don't really need the subscript because this is going to keep going forever. And I'm probably going to need more room. Okay, well, I'm just going to try to leave it, and hopefully I have enough room. Here we go. The first term, e to the 10th. We're going to need first 4 non-zero terms and the general term. Then the next one would be 5 e to the 10th. Then we have the x minus 2. Then the next one was 25 e to the 10th, x minus 2 squared. That one was over the 2 factorial. Ooh, there we go. One more non-zero term, plus, then we had the 125 e to the 10th, and we had the x minus 2 cubed over the 3 factorial. This is going to be close, plus dot, 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 plus, and let's get the general term, which is right there. So I'm going to have a 5 to the nth times e to the 10th times my x minus 2 to the nth over the n factorial. We're just writing that nth term, we're just adding it. And then what we need, don't forget plus dot, dot, dot. I kind of squeezed it in. After the general term, we need to put the plus dot, dot, because this series goes on forever. Remember, the polynomial stops at whatever term it tells you the degree is, but the series, you have the polynomial, put dot, 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 then you need the general term, and then plus dot, 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 because it keeps going forever. The series is like the polynomial, but it keeps going forever, which means I'm going to need to write out some non-zero terms. Here it says 1, 2, 3, 4, right? So we have 4 non-zero terms, then the general term, and then do not forget the plus dot, dot, dot after the general term. Because if you stop it with the general term, it's a polynomial, you're going to get it wrong, right? Which is mean, but you're going to get it wrong. All right, so that's how we can build a Taylor series. And a MacLaurin series would just be a center of 0. So you'd have x minus 0 squared, so it would just be x squared, x cubed, x to the 4th. Right? Remember, MacLaurin is just a special case of Taylor where it's centered at the origin. Now, there's 3 really common MacLaurin series that you're going to want to know. And we're going to go through and we're going to build them. And then these are ones that you probably are not going to want to have to rebuild again. So these are ones that you're going to want to just remember. We're going to go through and we're going to build the MacLaurin expansion for e to the x, then the MacLaurin expansion for sine of x, and then we'll do the MacLaurin also for, you guessed it, cosine. E, sine, and cosine. Those are the MacLaurin expansions that you're going to want to have memorized. We're going to build them now, but then hopefully in the future we don't have to build them anymore. All right, let's go for it. Let's build this this MacLaurin series, which is a Taylor series. Let's build it for e of x. Now let's see, the original function. Actually, let me do it over here so it's a little bit more room. So the original function is e to the x, right? The derivative, e to the x. And then your second derivative, e to the x. Are you bored yet? We'll do one more. The third derivative, e to the x. Okay, dot, dot, dot. Let's look at the nth derivative. E to the x. Boring. Okay, very good. Here we go. Now we would evaluate all of those at the center. Remember, MacLaurin means the center's at 0. E to the 0 is 1. So that's 1. That's 1. That's 1. Right? They're all going to be 1. Any nth derivative, when I evaluate it at the center, is always going to be 1. And then we just need to tack on all the extra stuff. Right? Here we would tack on x over 0 factorial. Come on, smart board. You're really making me angry today. But we'd have x minus 0 to the 0th power. Right? Because remember, we have x minus the c to the nth power over the nth factorial. But when n equals 0, everything's 1. So you don't need to write it. Okay, so here we go. I'm going to try to erase that, but not get rid of everything else. Then I'm going to need x over 1 factorial. But that's just 1, so you can just write over. You can just write times x. And that one's going to be x squared over the 2 factorial, x cubed over the 3 factorial, and then dot, 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 the general term, you're going to have x to the n over n factorial. Remember, the first one's n equals 0, don't need to write times 1. The second one, you don't need to the first power, don't need the first factorial at the bottom. There we go. Now let's collect all these terms and let's get this MacLaurin expansion. The first term for my MacLaurin expansion of e is 1. Then I have 1x. Then I have x squared over 2 factorial. And then let's do the next one, x cubed over 3 factorial. You see in the pattern? The next one, 4x to the 4th over 4 factorial, and x to the 5th over 5 factorial, right? It's just going to be all that same stuff, right? Plus dot, 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 right? First 3 or 4 terms is usually enough for you to get the pattern. The general term is x to the n over n factorial, and don't forget the dot, dot, dot. And that is our MacLaurin expansion for the function e of x. And that is actually going to converge for all real numbers. That's really very nice. That's good news for us. That means we can pretty much always use this expansion. If we have to do something and somehow we just don't want to work with the function e to the x, well, we could use the polynomial. We could use this Taylor series as MacLaurin series instead, and it's always going to converge. It converges for all real numbers. You do not need to do the ratio test to check it. if you use the expansion for e to the x, you can always just assume and know that it's going to work for all real numbers. But there we go. There's our expansion for e. It has everything, right? 1, x, x squared over 2 factorial, x cubed over 3 factorial, right? Don't change that to 6. Don't change the next denominator to whatever, right? Leave the factorials as 2 factorial, 3 factorial, because then it helps you see the pattern. It's the nth factorial. Right, so there we go. That's our expansion for e. Now we're going to go through and we're going to do the same expansions for sine and cosine. Okay, let's get out of here. All right, let's build this sucker. Let's go take our derivatives again. Here's the original function. And so let's see, we're going to evaluate it at the center. Let's go take some derivatives. So that's the original function. First derivative, second, we've done this kind of before, third, fourth, and then that's probably going to be okay. And then here we go. Let's go take these derivatives. That would be cosine, negative sine, negative cosine. Back to where we started, sine of x. We could keep going, but we're really going to be okay. We're going to stop there. And then we would need to evaluate all of those at the center, which is 0. Sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0, that's negative 0. That's 0. Negative cosine of 0, that's negative 1. And this is going to keep alternating like that. 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. Where the x I am. Okay, and we just keep going through those same 4 numbers, 0, 1, 0, negative 1, over and over again, because these derivatives are just going to keep repeating in that exact same cycle. So the coefficients are just going to keep bouncing back and forth, 0, 1, 0, negative 1, 0, 1, 0, negative 1. All right, so let's go tackle on the stuff that we need to. That would be, remember you'd have like x minus 0 to the 0 factorial, or x minus 0 to the 0 over 0 factorial. Okay, I'm going to be done writing that. You don't need to tack on stuff for the original function piece. For the first derivative piece, you would need just the x over the 1 factorial. Okay, and then we'd have the x squared over the 2 factorial. Then we'd have the x cubed over the 3 factorial. X to the 4th over the 5 factorial. And then let's look, like which terms end up canceling. Well, the original function would cancel because it's 0. And that would cancel. And that one would cancel. Notice all of the even-powered terms are going to end up canceling. So this expansion for sine, the first term is actually going to start as 1x. Right? It starts with 1x. And then we're going to have the next term is minus x cubed over 3 factorial. The next term, if you remember from a couple classes ago, we have plus x to the 5th over 5 factorial. The next one would be minus x to the 7th over 7 factorial. We'll do plus dot dot dot, and then we'll look at the general term. Okay, now the general term's a little bit harder here, but we have to somehow write a pattern that describes what we're seeing. And what we're seeing is all the odd terms. Now, and this really is going to be like the 0th term for that expansion. That's going to be 1. That's going to be 2. That's going to be 3. So somehow we have to use that index, starting with 0, then counting up by in whole numbers. We have to use that to end up getting a pattern to describe this general formula. It's going to alternate, right? Plus, minus, plus, minus. So it's going to alternate. I know how to make that happen. -1, and let's check. You're either going to start it with n or n plus 1, based on whether we need the first one to be positive or negative. The first one is n equals 0, and I need that first one to be positive, so that's good, right? If you needed the term to start negative, then you could do something like that. But this is fine. Right? -1 to the n, that's going to take care of the alternatingness of it. And then I'm going to have, okay, sorry, I had to pause it because they were releasing for the end of the day, and it was just sort of been annoying. Anyways, all right, let's try to keep generating this pattern. Notice n equals 1 produces 1 as the exponent, 1 equals 3 as the exponent, 2 equals 5. It's only odd numbers. And how we can generate odds is stuff like this, 2n plus 1, 2n plus 1, or 2n minus 1. Those are the 2 easiest ways to always guarantee that you're going to have an odd term. So 2n plus 1, that's actually what we want. And then notice the exponent in that factorial match. So here I'm going to want a 2n plus 1 factorial. And then there we go, right? We've got that general term. It was a little bit harder, but we're just finding the pattern that fits all of those specific terms. And also this MacLaurin expansion for sine, it's also going to end up converging for all real numbers. It's really nice. Cosine 1 is also going to be all real numbers. Notice the sine is only the odd powers, right? And it alternates. So x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. It's going to alternate. Starts with the positive, starts with the x, alternates, and it's the only odd powers. All the even ones ended up canceling. Now, when we do the cosine, it's going to look a little bit different. So let's go for it. Let's flip it over to the next page, and let us do this expansion for cosine of x. All right, here we go. Let's take some derivatives. Again, this is kind of the same thing. Here my original function's f, the derivative, negative sine. Then the second derivative would be negative cosine. Then the third derivative would be sine. And then the fourth derivative would be back to cosine. Okay, and then you would just keep repeating over and over and over again. Okay, so those are just going to keep cycling. And then let's evaluate them all at the center. Cosine of 0 is 1, then 0, then negative 1, then 0, then 1. All right, so it's these same values. It's just starting at a different point in the process. All right, so let's tackle on the stuff. This one is going to need x to the 0 over 0 factorial, so nothing. That one need x over 1. That one's going to be x squared over the 2 factorial. That one's x cubed over the 3 factorial. X to the 4th over the 4 factorial. Let's look at what terms cancel here. That one's gone. That one's gone. So it's the odd powered terms that canceled, leaving us with the even powered ones left over. So here we go, the cosine expansion. It's going to end up being 1. It kind of starts as 1 is like the 0th power. It's lumped in with the evens. Minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. We didn't take 2 more derivatives, but we could have. Plus x to the, actually, let's just do plus. I like always doing a plus, dot, dot, dot. By the way, you could do a minus, dot, 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 or plus. It doesn't matter. Then we need the general term. It's going to alternate. So again, I need the negative 1. I need it to start with an, that's, again, n equals 0. This is n equals 1, n equals 2, n equals 3. I need to start with the positive. So I'm just going to have negative 1 to the n. That's the easiest way to make something alternate and start positive. And then I'm going to have even powers. So this is going to be x to the 2n over 2n factorial. So there's your expansion for cosine, and it's also going to work for all real numbers. Okay, so the exponential was everything, and it was all positive. 1 plus x squared over 2 factorial plus right dot, dot, dot. All positive, and you had all of them. That was the e exponential, the expansion. The sine, it's going to alternate. Starts positive, but it alternates, and it's only the odd powered terms. So we had x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, right? Plus, minus, and then the cosine here, this last one. It's going to be only the even powered terms. And the constant 1 is lumped in with the even powered terms, and it alternates. E is always positive. Sine and cosine alternate. Sine is the odds. Cosine is the evens. Those expansions you're going to want to know. The expansions for E, sine, and cosine you're going to want to know. Now, here are some other ones that come up fairly frequently. You wouldn't really need to have these memorized, but they do come up. I just noticed a couple years ago when I was doing all my homework keys, like some of these just came up frequently. Okay, so these are just extra ones that you can kind of keep at your reference, at your disposal. They come up periodically, okay, and so there they are for you, right? They're there. We're going to talk a little bit more about some of these ones. In particular, stuff like this we're going to talk about later and how it's kind of going to be like a geometric. But yeah, we could always just take derivatives, build stuff from scratch, tack on the stuff we need to tack on. Like we could, based on any function, right? Any of those, we could just take the derivatives and then build it from scratch. But if you can just remember what those are, or if you can look them up, then it'll save you a little bit of time. But again, these two we're going to talk and deal more with here in a little while. But the E expansion, sine expansion, and cosine expansion. Those are some biggies, and you need to know what those three are. These extra ones, you will probably be able to either prove them whenever you need them, or they'll be given to you, or you'll be able to look them up. All right, but that kind of wraps up the stuff that we should have probably gotten through last time. And so I'm going to actually end this video right now, so for future use I can use it. And then I'm going to go ahead and pick up with this next example in the next video.